when you restrict everything to xy plane, the region is very nice for polar coordinates. So there it is begging to be passed to polar coordinates. We'll do that. Okay. Okay, so first we integrate this part. Okay, so this part. So this is equal to 4 times. Okay, so 4 times 0 to 2, 0 to 4 minus z squared. This is constant with respect to y. Okay, so this is constant with respect to y, so this is x squared plus z squared, y. Y from x squared plus z squared to 4. Okay, then we have dx dz. So let me write one more step. So this is going to be, in our case, 4, 0 to 2, 0 to 4 minus z squared. I have this x squared plus z squared to the power 1 over 2 and this. So this is going to be 4 minus x squared plus z squared to the power 3 over 2. Right? dx, dy, dz. Okay, so now you see that it's very painful to continue in this way, but you can pass to polar coordinates. So I'll leave it as an exercise to you. Pass to polar coordinates. But polar coordinates has to do with x and z, so you have to be creative here. Okay, so let's say x equals r cos theta. Okay, we are trying to express everything here in terms of r and theta. Okay, so you can choose it in any way you like. So since it depends on which way you are looking at it this way. If you look at it this way, then you should consider zx. If you look at it from this side, then it is xz. So algebraically, I'll just write x equals r cos theta, z equals r sine theta. Okay, so from there you see that dx dz in any order will be r dr d theta. Here you have r squared. Here you have what, 4 minus. Here you have the equation of the circle, but of course this part will be different. Okay, your r goes from 0 to 2, and your theta goes from 0 to pi over 2. Okay, so that part I'll leave as an exercise because I have more interesting integrals. Okay, so this one, these are more interesting. Okay, so let me do this problem now. Bounded by the paraboloid z equals 4 minus 3x squared minus 2y squared on the top. Okay, so this is a paraboloid going downwards. Okay, so when xy is 0, z is 4, and then when xy is different than 0, this becomes smaller. So it's just like an umbrella going down like this. So this is bounding our region from the top. We call these things paraboloid because when you project this to one of the coordinate planes in the, when x is equal to 0, we are looking at here in the yz plane. So you see that in the yz plane, this is a parabola. Okay, so that's why we call these things paraboloid. And by the paraboloid z equals x squared plus y squared at the bottom. Okay, so this is now a paraboloid going up. They intersect along a curve in space. So the space is not just a circle like this. Okay, so it goes up and down. Well, not much, but it doesn't lie in a plane. So the task here is to sketch the region and find the projection of this intersection curve on the xy plane. Okay, so maybe the intersection in 3 space will be something like this. You project it onto xy plane. Okay, it will be something else there, maybe a circle, maybe an ellipse. Okay, and then that will be the domain there. It's the rest of, once we do that, the rest will be easy. To set up the integral will be trivial because it's already given that an arrow parallel to z-axis typically intersects the region at this surface and leaves the region at this surface. And the tricky part was to decide where the bottom of this arrow moves. It will move inside the shadow of this curve of intersection. Okay, and then once we decide what the region in the xy plane is, we'll find the domain. We'll find arrows parallel to x and y, and we'll find how it enters the region and leaves the region. That reduces the problem to double integrals. Okay, so the picture is something like this. Now this is, at first there's no reason to expect that this is symmetric, but it is symmetric because you see this doesn't bother on the signs of x and y. But anyway, so one of the surfaces is something like this, paraboloid. The other one is, so let me draw the other one with a different color, maybe it helps for me to understand what's happening. Okay, so let me look at the picture. One side is up, so I think that side is up. So I'll take this side a little bit more down. Okay, and then we have the other paraboloid like this. Okay, the line of intersection is, the curve of intersection is something like this. Okay, so it is something like this. Now this part is z equals 4 minus 3 x squared minus 2 y squared. And this part is z equals x squared plus y squared. When they intersect, the z coordinates will be the same. Okay, so curve of intersection lies on the cylindrical surface obtained by eliminating, I'm writing this only once, in other problems this goes through your mind within a split of a second and you apply, by eliminating z from z equals 4 minus 3 x squared minus 2 y squared and z equals x squared plus y squared. Okay, so when you eliminate them you get, okay, so 4 minus 3 x squared minus 2 y squared equals x squared plus y squared. So the cylindrical surface is, well, this is the cylindrical surface, but after you simplify it, you have, let us take this to the other side, we have 4x squared plus 3y squared equals 4. Now, if we were only in the plane, this is an ellipse, okay? But we are in R3, z coordinate is free, so those things we call cylindrical surfaces. Okay, so you should take a look in the book on the section where there are very nice pictures of cylindrical surfaces, just to remember. So what's happening is that when you project this down here, we get an ellipse. Well, I have the ellipse here, but okay, let me do it here. We have this ellipse here, this part of the ellipse, and we have this cylindrical surface. Okay, so this orange thing is a cylindrical surface, and this part, this common intersection, lies on this surface. Okay, so the two surfaces. Now this surface z equals x squared plus y squared. touches this cylindrical surface here, and then it goes out. And similarly, the other one is inside, it comes here, and then it goes out like this. Okay, so you see that this part does not lie in a plane z equals something. It lies on this surface. And its projection is here. So now in the xy plane, we have 4x squared plus 3y squared equals 4. This is an ellipse, if you want to recognize it. Okay, so now we have almost everything except that let us find the coordinates here. The coordinate here is x equals 0, so y is 2 over square root 3. So this is, let me just write 2 over square root 3. It is understood that this is the y thing. The x thing is when y is equal to 0, x is 1. Okay, so everything is resolved here. And since we are interested in the volume, the function is 1. We will look at the function 1. So 1, it doesn't tell us, it doesn't dictate us any order of integration. You can use anything. The picture tells us that if we should start, to make life easier, we should start integrating with respect to z. In that case, an arrow from here, okay, now I'm seeing this orange is not there. I see the arrow. It enters the region here. It is inside the region, and then it goes out. Okay, so I know description for these points, and this one is inside here, and I can explicitly write the limits of integration inside this region. So let's see what I did here. Okay, so let me write it over there. So again, I decided that if I calculate this volume and multiply it by 4, it will be the same. So check this judgment. Okay, so my judgment is that this is symmetric. So I integrate with respect to z first. So I know the limit. It starts from x squared plus y squared. It goes to 4 minus 3x squared minus 2y squared. 2y squared. Next, inside, well, I can integrate, I can do this in any way, either way. So here in my notes, I integrated this with respect to x. So x enters the region, the arrow parallel to x-axis enters the region when x is equal to 0. Okay, so we are looking at this arrow now. Okay, it enters the region when x is equal to 0 and leaves here, and I have to solve for x. So that is square root 1 minus 3y squared over 4. Okay, just solving x from here or from here. Okay, 4 minus 3y squared divided by 4, take square root, that's your x. And then we integrate with respect to y, so everything is collapsed to y-axis, and the shadow is from 0 to 2 over square root 3. From 0 to 2 over square root 3. Okay, so this looks horrible, but actually it can be done. Okay, so what I did was 4 times these things, 0, 2 over square root 3, from 0 to 1 minus 3y squared over 4. And you have this thing. Okay, so we already subtracted them here, so we know the answer. The answer is 4 minus 4x squared minus 3y squared dx dy. Now we integrate this 4 from 0 to square root 3. I'm integrating with respect to x, so this is 4x minus 4 over 3 x cubed minus 3xy squared. From x equals 0 to x equals 1 minus 3y squared over 4 dy. So you simplify this. Okay, apparently I skip several steps here. You put this thing, simplify, and when you simplify, you will have 4/3 square root 4 minus 3y square minus y square 4 minus 3y square. You integrate this with respect to y. Okay, how do you integrate this? It's begging for trigonometric substitution. Okay, so you put y equals a constant times sine or cosine, so that this thing comes out, and then you get a trigonometric integral, which you can do. So I'll just write the result for you to check. Okay, so here I suggest with the integrals, of course, there is no, you can also try your luck with these things. Okay, you can guess once you have something like this. So try y equals what, 2 over square root 3 sine theta. Okay, so everything becomes trigonometric. So here you'll have sine, here you'll have cosine, here you'll have cosine, and here you'll have sine. So it looks easier. There's a chance that you can integrate. And of course, that explains why we had pi here. Okay, so there's no pi in the problem, and in the answer there is pi. With polar coordinates, you won't get anything easier. Yes, you can pass to polar coordinates, but when you have 4 cosine square plus 3 cosine square remains like that, okay, then there's no big advantage to passing polar coordinates. If they were both 4, then sine square cosine square is 1, and you throw away all the squares, and things simplify. Okay, so here we don't expect that, but you can try. Well, this is integration. You can try passing to polar coordinates here, and now you have r and theta. Maybe it will be easier. Okay. Okay, this one I want to do because this one we will write the integral in all 6 possible ways, and after that I'll just sketch one volume and leave it as an exercise. Then we'll have our quiz. It turned out that our assistant is giving you too little marks in the quizzes. Your average in the quizzes is the lowest. That's because of the assistant, I know. So I'll talk with them, and your next grades will approach to the average of the other sections. This is the first time he's reading quizzes, so that's always what we do. And the first time when I read quizzes, I corrected every mistake. And then I was reading homeworks, and every time there was a mistake, I was crossing out with a red and breaking down points. And finally, the instructor, the professor, decided not to give homeworks to the class because I was being a bad impact on the morale of the class. So instead of teaching me how to give generous grades, he just canceled all homeworks. Okay, so that's what's happening with our assistant. But I'll talk to him. I won't cancel quizzes. I'll talk to him that there are other parts where he can give grades. Okay, so this exercise is to show that we can switch the order of integration in 6 different ways, and sometimes the region is good for this. Okay, so write the integral (0 to 1) square root x to 1, 0 to 1 minus y, f of x, y, z. Well, let's skip the f part here. I don't want to write f 6 times. So dz, dy, dx. Okay, so the integral is easy. We can immediately calculate it in this order. But this is an exercise to write the integral, to change the order of integration in all possible ways. There are 6 permutations of these. One of them is already given like this. Now we want to write the others. Again, the way to start this is you sketch the region. Then by looking at the region, we write the other integrals. Okay. So first we sketch the region. Okay, let's see what the region is. Now, a typical arrow parallel to the z-axis enters the region when z is equal to 0, so this is the base, and it leaves the region when z equals 1 minus y. So we are talking about a plane, okay? z plus y equals 1 plane, okay? So we have this plane here. Not all of it is going to be used. The others will tell us what's happening. Now when we collapse this to the xy plane, a typical arrow parallel to y-axis enters the region when y is equal to x. Y is equal to square root x. So this is x squared is equal to y. So this is a parabola like this. Okay, let's draw this. This is our x squared equals y, or y equals square root x, depending on which way we want to see it. And it leaves the region when y is equal to 1. Okay, so y is 1 here. This is 1. Okay. And this point of intersection when y is equal to 1, x is equal to 1. Okay, so this is 1, 1. So this point is 1. When we collapse it here, we get this part, and the integral says use all of it. Okay, so the integral could tell us to integrate from 0 to 1 over 2. Okay, so then we would be only using this part. But now it says use all of this. So let us see what the plane was. We have this plane, okay, but we are using only this part of it. So the plane, you see, this is a cylindrical surface. Only 2 parameters are related to each other. The third parameter is free. So if you look at this line, this is z plus y equals 1. This is 1. Okay? And then it comes like this here. That's your cylindrical surface. This is another cylindrical surface. Okay? Because x and y are given, z is free. So this goes up. Those 2 cylindrical surfaces intersect along a curve like this. Okay, so this part is the plane. Okay, so this part is the plane, and this part is the cylindrical surface. This one, x squared equals y. So, okay, we totally understand the region. The region is this strange thing in the first octant. Okay, now let us reverse the order of integration. So this is one order is given. So, okay, let's say now we can write the integral in the other. Well, I didn't finish this slide. The integral in all possible orders of integration. Okay, so we sketch the region. Next, we can write the integral in the other orders. So let us say this integral I is, we'll write these things. So dz, dx, dy. Okay, then we have, let us now take dx down. We say we have dz, dy, and then we will have dx here. I change dz and dy, dy, dz, and I take dy first, dy, dx, dz, and finally I have dy, dz, dx. Okay, let's do that. We are integrating respect to z. Well, it's already here. It's from 0 to 1 minus y. Now I integrate with respect to z. With respect to x, I'm in the xy plane. So this is the region in the xy plane. An arrow parallel to x-axis enters the region when x is equal to 0. Leaves the region when... Bunu niye böyle yaptık ya? Okay. When x equals y square. Okay. And y is between 0 and 1. And you collapse this 0 and 1. Okay, now we integrate with respect to x. Okay, so now we have an arrow in the space parallel to x-axis. It enters the region here when x is equal to 0 and leaves the region along this surface where x is equal to y square. And bunu da düzeltelim. And now we call x coordinate is collapsed. Okay, we are in the yz plane. In the yz plane, we are integrating respect to z. So we start from here. We enter the region when z is equal to 0. Leave the region along this line when z is equal to 1 minus y. And y changes. Now you collapse it to y-axis. Y changes between 0 and 1. Okay, so this one, the first one is 0 y square. Okay, now you tell me what y is. Now we collapse everything to yz plane. Now I take an arrow parallel to y-axis. It enters the region when y is 0. Where am I? Here. It leaves the region along this line. Y is 1 minus z. And z changes between 0 and 1. Okay, so again, you collapse this here, and you see that all of this is used. Okay, now we start with y. We consider an arrow parallel to y-axis. It enters the region along this surface, where y is given as square root of x. It leaves the region along this surface, where y is 1 minus z. Now we collapse everything. We integrate with respect to y, so we collapse everything to xz region. Okay, so what is the curve here? Okay. What is the shadow of this? What is the shadow of this here? Okay, so hemen kurtulmaya çalışıyoruz. Okay, so what is the shadow of that there? Which one is this? dx, dy, dz. I'll ask a more complicated question in the quiz than this one. So you should find the relation between x and z. Well, I think we wrote this. Curve of intersection lies on this blah blah blah. You do the same thing. You eliminate something from here. When we are in the xz plane, we eliminate y. Okay. Here y is equal to 1 minus z. If you are traveling on this. On this one, y is equal to square root of x. So here, when you eliminate them, you'll get an equation. Tell me. Z plus square root of x equals 1. Okay, so it's something like this. So this is x square equals 1 minus z square. So this is a parabola. When z is equal to 0, we are here. When z is equal to 0, we are here. When z is 1, x is 0. So it is something like this. And it's x. Okay. So let's go back to where we are. We are here. Now x starts from 0 and goes to this. X starts from 0 and goes to 1 minus z square. And z changes between 0 and 1. Okay. And I leave it as an exercise because now once we know this, well, okay, let's do this. We know y is from square root of x to 1 minus z. Z now goes from 0 to 1 minus square root of x. From 0, 1 minus square root of x. This is 0 to 1. Okay. And which one is the easiest of these to calculate for you? I thought this one, I found this one is easier. Well, each of them is easy, but this one for me is easier because I'm integrating with respect to this. I get y's. Y is constant with this. I integrate. Integration is simple until you come to the last part. In the last part, you integrate a polynomial of y, and you get 1 over 12. Okay? So the answer is 1 over 12. Just check. Okay, now I was going to give you another problem, but that I will do later. So now let us have our quiz.